Hello and welcome to Easy Projects. In the last video we started to look at LEDs and how to drive them. We looked at what happened if you don't have some sort of a current limit in form of a resistor or a constant current drive. We learned that for normal LED indication lights we can just use a standard resistor to limit the current, but for high power or high efficiency circuits we would like to use a constant current source. And so in this video we will look at exactly that. And a constant current source we can draw as an arrow. I said in the previous video that we would look at a switch mode, a constant current supply, and we will indeed do that, but I think it will make sense to include the linear version also. So it's a bit unfortunate for us right now that most supplies come as a constant voltage supply. If you buy a plug pack or wall wart, it will have a voltage written on it, and your batteries will come at a certain voltage. So we have to convert it from a voltage to a current somehow. There's two different types to mention. We have a constant current source, but we can also have a constant current sink. It just depends on which side of the load you put your regulator. This regulator will regulate the current with reference to the positive rail, and this regulator will regulate with reference to the negative rail. Kind of similar to transistors, that if we just forget this is LEDs and you want to turn it on, you would put a PNP transistor in this position or an NPN transistor in this position. So these constant current supplies can be made in a lot of different ways, but we will look at a few of the simple ones. So one that I like is a constant current sink, and it uses an NPN transistor. It has a emitter resistor to ground, and we rely on the fact that a known voltage across a known resistor will give a known current. So if we say that this is, for example, 10 ohms, and we know that the emitter voltage is related to the base voltage. So if we can somehow control the base voltage, we can also control the emitter voltage. And we can do that with a reference. It could be a Zener diode. Now we just need to apply a high enough voltage here through a resistor. Otherwise we would burn out the Zener diode. And we need to select the Zener voltage or the resistance here to set the constant current. So say we have a 3.3 volt Zener diode. We know that the transistor will have a voltage drop from the base to the emitter, approximately 0.6 to 0.7 volts depending on the transistor. Let's say 0.7. We know that we will have 3.3 volts right here because of the Zener diode. So if we subtract 0.7, we will get the voltage on the top side of the resistor, and we can then calculate the current through it. So this point is 2.6 volts, and 2.6 volts divided by 10 ohms is 260 milliamps. That is a bit on the high side for a small LED like this, but probably what you would want for something like this. We can easily optimize this circuit though. Remember, this is a linear regulator, so all the power that's not used to light up the LED will be lost as heat. If we say this LED has a drop of 2 volts, just to make the calculation easy, we can subtract the 2 volt from 12, we have 10 volts, and we know that the current would be 260 milliamps. If we multiply those two, we see that the loss is 2.6 watts of the dissipated energy. That is very, very inefficient. To improve it, we could just drop the 12 volts all the way down until we just have enough voltage to get the full current through the LED. You can see that we wouldn't be able to go lower than 5 volts because we have 2.6 volts across this resistor. In this configuration we need to have that to have the correct current. But nothing really is stopping us from lowering the resistance value and lowering the reference voltage. For the silicon transistor like this, we need something higher than 0.7 volts because we will lose that across the base emitter junction. But we can use 2 normal diodes instead of the Zener diode and put them in series like this, which would give us about 1.4 volts. The reason we use 2 is because if you look at it, we have 1 drop here and we get another drop from the extra diode. So we get approximately 0.7 volts here instead of the 2.6. Let me draw it on another page. So just to repeat, we changed the reference from a Zener diode to 2 normal silicon diodes. They still provide a somewhat reliable reference if we keep the current the same. There's no doubt that a proper reference here would be better, but normally it's not really needed, that high precision. This creates 1.4 volts at this node, and we drop 0.7 volts across the base emitter junction of this transistor, and that leaves us with 0.7 volts to go across this resistor that we haven't selected yet. But if we want the same 260 milliamps, we know that the voltage divided by the current will give us the resistance value, and that gives me 2.7 ohms. So what about this resistor here? It's a bit more complicated, it might look, to find the right value, but it's not really. If this voltage gets below 1.4 volts, this will simply not be there. So up until that point, we don't even have to consider this. And what determines the current here is the base current and times the gain of the transistor plus 1 base current. So we have the base current and plus the base current times the gain of the transistor. That's the current going from here. And it's a bit difficult to say with certainty what that is. You can look up the datasheet and it will give a value from maybe 50 to 350. So you can't really count on that. You have to take the minimum value and you can use that. So in the case of a minimum gain of 50, we would take our current here, 260 milliamps, divided by 50, and that gives us the current that as a minimum needs to flow through here. So that is 5.2 milliamps that we need to be able to supply into the base here, and that would depend on this voltage. So we have to set this voltage first, and then we can select the resistor here. But the good thing about it is if you increase the voltage, it doesn't affect the current, it just affects the power dissipation. So just a quick calculation, if we set a 5 volt supply, we would need a 692 ohm resistor here to give us the current that we want. But I want to make it with slightly less power, so I will make a new one for the 20 milliamp diode. So I just did the same calculations again, and it turns out for 20 milliamps we need a, I think it was 35 ohm resistor. I just rounded down to 33 ohms. And the base resistor here is maximum 9K for a gain of 50. It wasn't specified for 20 milliamps for this transistor. It's a 2N3904 that I will use. It was specified for 10 milliamps or for 50 milliamps, so I just kind of took an average. It's pretty much just a guess, so don't rely on it. So I have built up the circuit here. Basically it looks exactly like our schematic. We have a 33 ohm resistor here. We have the transistor here, the LED here, and I selected an 8.2 kilo ohm resistor. That's the highest one I have, below 9 kilo ohm. And we have the two diodes here. So let's see what happens when we turn on the power. It looks like our LED didn't explode, and I apply 5 volts across it. If we didn't limit the current, if we just had the LED and the 33 ohm resistor at 5 volts, it would blow up. So if we look at the power supply, we see 5 volts and 19 milliamps, 19.5. It's close enough. And actually, I will confess that I cheated a bit, because the first diodes that I used are here. These are 1N 4007, I think. Yes, 1N 4007. These do not have a voltage drop of 0.7 volts when we apply this low current. So I did get only 10 milliamps from the LED. I found some other diodes in my collection here that does have almost 0.7 volt drop. And that is why I now get 20 milliamps. So I hope you will be able to see everything at once. And if we start by measuring the voltage drop across the diodes here, we expect 1.4 volts. And we almost get that. We can measure the individual one, and that's, you see, not quite 0.7, but it's close enough. And these two diodes, that's the main regulation of the entire circuit. So if these are off, then the current will be off. That's why it's better to use a dedicated reference, but that would be pretty expensive, and we want to keep this as a low-cost circuit. As long as you know exactly what this voltage will be, you can calculate all the rest. The drop across the transistor, it's also important, but I find these are a bit more stable around the 0.7 volts. Or maybe I just get used to use this particular transistor. I'm not really sure. But if this voltage varies, then the current will vary also. But the true test is not really to show you that it delivers 20 milliamps. The true test is to increase the voltage and see what happens. So this is at 5 volts, and if we go to 6 volts, you can see it doesn't really regulate that well. Oh, that was 6 volts. 7, 8, 9, 10. You see, it's not completely stable at 20 milliamps. And we can go down 4 volts, even 3 volts, and if we go to 2, it will die, obviously. So what is happening here, you might ask? And again, it's exactly the same as we discussed before. If the voltage at this point is not the same, then the current will not be the same. And that's the disadvantage of using diodes, is that when the current changes, the voltage will change also. And the current does change when we apply more voltage from the supply, because we get more current through this resistor, and all the excess current that doesn't go through the transistor will be burned off in the diodes. So that increases the voltage and increases the amount of current that can go through the transistor. And if you want a current source instead of a current sink, you can make that exactly the same, just using a PNP transistor instead and flipping everything. It's the same values and components except for the transistor, and then the location has been swapped to reference the high side. It gives exactly the same result, except I was very lucky to hit exactly 20 milliamps. It's just because of the slight variations in the transistor. Last time we had 19.5, now we have 20. It's also not completely stable. As you see, if I increase the voltage, we slightly increase the current. Since it is a constant current supply, we can also change the color of the LED. It doesn't really matter. And also a blue LED. Just note that the blue LED has a greater forward voltage, so now we are operating at 5 volts, but if we were operating at, say, 4 volts, maybe it cannot give enough current to the blue LED, because we do still need the minimum voltage. It's also possible to put more LEDs in series, and we will still keep the same current. So as long as you have the forward voltage of the LEDs plus the margin for the regulator or the dropout, then it will work. But you can see if I drop it to 7 volts, the current drops because it cannot supply enough. And if we find the voltage where it just starts to drop out, about 7.5 volts, if we compare that to the actual forward voltage of the LEDs, it's 6.7. So the regulator has a dropout of 0.8 volts. So the dropout of the regulator remains constant, and you can then say that the more LEDs in series we add, the greater efficiency we get, as long as we keep the supply voltage just where it will regulate. So for one LED it's about 66% efficient, and for 3 LEDs it's much more, actually about 80 to 90%. But of course we wouldn't drive it right at the edge of dropping out of regulation, so we might add a bit and get 75% efficiency out of this. But again, it's not always that you can select the supply voltage yourself. If the rest of your system runs on 12 volts, well, then you kind of normally just use 12 volts to drive your LEDs also. And with a normal current limiting resistor, you get down to 5–10% efficiency. And in that situation, this circuit will not save you. It will be the same efficiency. And so that's when we get into the switch mode converters. But first let's take a look at some more linear ones. If we keep the same idea of controlling the voltage across a resistor to set the current, we can build something very similar to this. But instead of using 2 diodes to set the reference, we can actually use a transistor. Remember, here we need to have a reference greater than the base emitter or emitter base junction in order for any current to flow. If we use a different transistor to set the voltage across this resistor, then we can get a lower value, and that will be determined by the emitter base junction of another transistor. So you can see here that there can never be more than 0.7 volts across the resistor, because if there tries to be, it will just go through this junction instead. Of course, if we don't limit the current by other means, then we would just burn out the transistor, because it's just a diode. So what we do is we limit this current with this transistor, and this current going through here needs somewhere to go. If we connect it up to this transistor, it will try to block this. So remember, the PNP, the current flows from the emitter to the base, but it can only do that if the base is 0.7 volts lower than the emitter. And if this transistor up here tries to turn on, it puts more voltage here and it turns off this transistor, which in turn turns off this transistor. So it's kind of self-balancing. The thing that then lets it work is a small, or I should say a large resistance to ground, resulting in a small current to ground. So I built up the circuit here real quick. It might be a bit harder to understand, I don't know, at least it was for me in the beginning, like how it all works, but it's a bit simpler. It uses only 4 components, and the most important thing probably is if we look at the power supply. We are at 18.5 milliamps at 5 volts. We can go down a bit, it drops a little bit, and we can go up. And as you see, it's pretty stable. It's more stable than the previous one. Or I should say it's regulating the current better when the voltage varies. So even though we found a slightly better one for the same cost, the disadvantage of both is that the current is not easily adjustable, because it's set by this resistor. For low power, low current, you can use a potentiometer, that would be fine. But for higher current, that requires a potentiometer that can handle that current, and that can be quite expensive and hard to get. So could we make a circuit in a way that allows us to adjust the current by a low power potentiometer, and then the regulator would rely on fixed components? So if we allow ourselves to use an op-amp, then it's pretty easy. So the op-amp will always try to keep the two inputs the same. And if we set a voltage on the non-inverting input, then the op-amp will adjust the output to get the inverting input to the same potential. Within limits, of course. It will do it if it's possible. So the output controls this transistor, and the inverting input sets a voltage across this resistor. It's the same principle as before. Now we can just adjust the current. And you can use this to make a constant current load if you want. And it can be used as a constant current driver for an LED, or a motor, or whatever you want. And I guess I have to mention it, there's always the classic one using the LM317 voltage regulator. We can kind of abuse the way that it's regulating to make it into a current regulator also. Because the adjust pin wants to see 1.25 volts less than the output, we can tie it to the output but put a resistor in series, so it will make a voltage drop across the resistor of, I think it's 1.25 volts, maybe it's 1.2, and that sets the current. The only disadvantage is the LM317 is more expensive than transistors, and again it's not easily adjustable with the low value resistor here. It can definitely be done with a wire wound potentiometer, but again that's quite expensive, so it might not be the option that you want. Of course, the option to go with if you are manufacturing a product in higher volumes is of course just to buy an IC that does the job. They are pretty cheap, maybe even cheaper than the regulator here. Just again, if you want a fixed current, maybe a circuit like this would be cheaper than the IC, but again then you would have to design and test it. Consider if your time is worth more than the cost of the IC. That's always the trade-off. So now we covered some of the linear current regulators. I'm sorry I can't really cover everything, and the video would be 10 hours. But yeah, sure, feel free to leave your favorite one in the comments if I didn't mention it. And see you soon for the next video, where we'll be looking at switch mode constant current supplies. Thanks for watching this video, and see you soon.